Let's go ahead and look at a fundamental problem, even though the solution is in the back of your book already. We have a sphere keyword is going to roll without slipping another keyword. That means there's friction here. And we want to find the acceleration of the center of mass and the angular acceleration of the sphere. Okay, so for a sphere, we can say the moment of inertia is 2/5 ml squared. And I get 0.18 kilogram meter squared when I solve that. So let's then sum the moments, but let's look about the instantaneous center of zero velocity right here. To do that, we're going to have to sum the moments about, our kinetic moments about the instantaneous center. Alright, what moments do we have? Here's kind of the tricky part. Well, we have mass times gravity hanging down right here. I'm just going to draw that. If we have mg hanging down, we have some component perpendicular to the plane and some mg sine theta parallel to the plane. This one is concurrent through our center of mass and through our instantaneous center, so we don't have to consider it, but we do have to worry about the mg cosine theta. Because this thing right here is acting at a distance away, right? If this was sitting upright and the mass center was directly over the center, it's not going to go anywhere. As you start to tilt this, the mass center moves to one side, giving it some oomph to roll. Okay, sorry, not mg cosine, mg sine 30. And that's acting at 0.15 meters. That's the only moment we have being applied. If it was from rest, we might look at the frictional force here that's actually causing the moment, but we don't have to in this case. Let's just sum about right here. Yeah, so we wouldn't need the frictional force because it's concurrent with the instantaneous center. So there's a couple ways to solve this. In this method, we're not going to have to. We're just going to use I alpha, but then we have to consider mass times the acceleration due to gravity times the radius r. That's this part right there. Right, there's some extra stuff. That's our kinetic moment. Okay, I can get 20 times 9.81 times the sine of 30 times 1.5. That's all just a number. It's equal to 0.18 alpha plus 20 times the acceleration of g times 0.15. Alright, one equation right there, and we can get another from the acceleration of g being equal to alpha r. And we can say that's alpha times 0.15. Alright, we have two equations, two unknowns. We get alpha as 23.36. It's a positive direction, radians per second squared. And the acceleration of g as 3.5 meters per second, and it's down at an angle of 30 degrees. Or 180 plus 30, 210 degrees.